I need an audio behind it.
Okay, so now we're going to have a change of direction. I'm going to talk to you about speech recognition errors. All the talks you've heard so far today have been on the many sources, but where the sources were audio sources, they were working on the closed caption version of those audio sources, not the speech recognition output. And yet, as James said in his introduction, we're trying to build technology that will work in the real world where we don't have that. We can't count on that. And we were using a recognizer whose error rate on average is 27%, and that's in some sense misleading because it's a very wide variance. Some pieces are much better and some are much, much worse. We want to know whether we can just put the pieces together, a speech recognizer and the first story detection algorithms that you've been hearing about. We are encouraged by the fact that there have been other areas in which that seems to have worked. Information retrieval experiments degrade with speech recognition errors, but not substantially. TDT tracking experiments, the results degrade somewhat, but not dramatically. So that gave us reason to hope. We did some experiments to tease apart these issues, and so we took two versions of the audio data, the ASR version and the closed caption versions, and so we had two parallel sets of data. And we looked both at the training corpus and the development test corpus, and we ran against all this 3 different algorithms which sort of span the space in terms of different kinds of approaches. These are things you've heard about before. And so what kind of results did we get? We see here, in each case there are a pair of curves, and the one which is less good is always the speech recognition output, and the closed captioning is the better. And it's a pretty big gap. It's compared to what people were showing you before this morning, that's a significant difference, substantial difference anyway. And it also sort of tends to diverge up at one end, which in some of these cases. So here we had the baseline system that evolved with cosine and TF-IDF that Victor told you about. Here we have the Bayesian language model that Dan told you about, and here is Rose's work with new names. In all cases, speech recognition errors hurt. And we want to know, I mean, it's not entirely surprising that they would hurt, but why do they hurt so much? So let me let you listen to a sample of this. Oops. I didn't mean to do that. I have to click. No. What am I doing? Where's the mouse? I can't see the mouse. Okay.
Here on this hour's top stories, the FBI's added Eric Robert Rudolph to its 10 most wanted list. Rudolph, suspect in the fatal women's clinic bombing in January in Birmingham, Alabama. And the FBI is upping the reward for information leading to his arrest to $1 million.
Okay, so that was clear. This is a perfect human transcript of it. Here's what the speech recognizer says. And to help you understand where the errors are, we've capitalized the words that came out wrong, or we've put in asterisks where the recognizer just dropped something. So from the combination of capitals and asterisks, you can see there are an awful lot of errors in here. By our standard measures, that's 20% word error. A bit better than the average, I said, for the corpus of 27%. And you see it's really made a hash of things like the name. Eric Robert Rudolph becomes Gary Robert Burdoff. And it made these mistakes despite the fact that every word here is in the recognizer's vocabulary. And so we have some problems. If you look at the closed...
I suppose you were cheating then, right?
How so?
Well, I'm just wondering, I mean, Eric Robert Rudolph would be in an ordinary vocabulary. I mean,
This recognizer has a vocabulary of 50,929 words, and so the individual words, individual names of that are common enough.
And they are first names, that's the
Yeah, right. So now let's look at the closed caption by comparison. Here, by our standard measures, we have actually a higher error rate, but it turns out that the transcriber there got the name correctly, even put it in once by mistake, so it loses points here. Here we talk about his arrest, and here we're talking about Rudolph's arrest. So that the closed captioner was making mistakes, moved the word January from where it should have been over to this part of the sentence. None of these has anything to do with the ability to retrieve. That's why we do so much better on closed captions than we do on ASR output. You know, if we wanted to, manually analyze a bunch of stories, here are some typical differences between them: spelling errors or different conventions of spelling between the two. This would hurt in cross-media comparisons. It wouldn't hurt necessarily within a medium. Named entities, sometimes in addition to the errors, like we talked about a moment ago, there are also these inconsistencies of various kinds between the two. And those are going to, of course, impact the named entity-based approaches. All of the approaches have something to do with named entities. Rose's had a lot to do. So what lessons learned? Comes down to the bottom line. For a task that are as challenging as this, which is more challenging than the other ones I mentioned, you have to have better speech recognition, which keeps some people just, yes, sir.
How do you segment the audio streams into source?
This was a cheating thing done beforehand. James in an earlier slide said we had to have somehow take this half-hour broadcast and have it segmented. That was done by hand, so we didn't have the confounding effects of errors there. In the TDT project, there is actually research to do that automatic segmentation, but I don't have anything to show you in terms of how that would be done. Paul?
Any indication of what happens if you just train a cached language model off the most recent newspaper?
That would be a question that Dan would want to answer. Maybe. Is Dan here? No. Hold the question for later. Yeah. Oh, I didn't see him. There he is.
I'll mumble more loudly.
What do you mean by the most recent newspaper?
My suggestion is that the most recent text that's from print media is likely to have a set of words that are likely to occur in broadcast. Probably not for first story detection, unfortunately. But otherwise, if your speech recognition system knows all the words that were in this morning's newspaper, it's likely to do quite a bit better on the new news. In that case, it might even have Eric Robert Rudolph on its trigram list.
Yeah, I think that makes sense. We didn't change the language model used by the speech recognition. We just took transmission that was done.
Yeah, so I know that the various people in the TDT community have talked about this idea, sort of trying to dynamically adapt the language model as you go along. I have to admit, I don't know whether anybody has actually tried that. Certainly was not done for this.
The experiments we did at CMU for TDT2 suggest that segmentation is actually more important relative to speech recognition for the tracking task, and also did some experiments for detection as well. The idea, the intuition being that when you do sloppy segmentation, you miss some of the important names and keywords near the beginning of the story. What do you expect here for first story detection? Do you expect that to be the case as well?
I don't have a prediction for that. We tried to partition problems, and we look forward to seeing you solving the segmentation problem for us automatically.
Okay, so, oh, Mike.
Well, actually, you're dealing with professionally read news stories. And I once tried this, and professional news readers are very good about causing longer divorce between stories than they are between paragraphs. I was quite successful at segmenting the BBC broadcasts just by chopping at the end of silence.
David, in the TDT task, we found that the pause, I think there is more of a pause between, but it's not a real good indicator in general. Okay, so Hubert Jin from VPN Technologies is going to discuss some information, some results showing that perhaps we're done.
Just try to prove we have been working hard enough. So James mentioned this week-to-week progress. We were doing quite well in the first 2 weeks, and then third, fourth, and fifth, it seems to me that the curve has become heavier and heavier. It's hard to push it down. And I believe that there is a reason, because if you look at the tracking task and the first story detection task, there's a close relationship between the two. And this is the TDT tracking task. We were given a few on-topic stories to train the model, so that for the incoming stories, we can label them as either on the topic or off topic. That's the tracking task. And if you think that we have a perfect tracking task, then the first story detection will be quite easy. Just track those stories. If it's not tracked by the known topic, then it's a new story. And these are the mathematical formula between the probabilities. So first story miss, that means that story is being tracked by the other stories you've seen already in the past. So in this case, this is the probability that this story is tracked by some topic, and this is not tracked by that topic. And then that means if it's not tracked by all the topics that you already seen, and take the complement of that, that's the one that that story is tracked by at least one of the topics you've seen already. And similarly, you will have this false alarm rate. That means the same topic, the first story and the following stories on the same topic failed to track this story, and this story is also not tracked by any other topics you've seen in the past. So this is, at any given time, we can have the probability miss and the false alarm. And then, because we deal with topic-weighted first story detection, then this is an exact equation, because it can take the probability of miss, that's the average of all the first story miss, probability of all the first story miss per topic. And the false alarm rate, this is kind of approximation, because the on-topic story that is not the first one coming in at random. So at any time, it could be once you see 7 or 6 topic already, there comes an old story on the second topic. So this is kind of approximation, and it would be better it will be better result if we can look at the lower bound and the upper bound for this quantity. But this is a good approximation at this moment. Yes.
This assumes independence of recursion. That's probably worse.
Yeah. That's the cluster-based algorithm is doing at this moment. And then here in this plot we show 2 curves. One is the TDT tracking task. The other one is the first story detection curve. That I pick one of the best ones. And the green one is the TDT tracking task, and the blue one is the first story detection. Now on the tracking task, I pick some points that's A to H, and then I convert it by the formula that I have on the previous slides into A to H, and then I connect the dots. And so this black solid line will be the expected performance of first story detection. As you can see here, it aligns pretty well with the blue curve, which is the first story detection curve we have at this moment. And it's well within the confidence interval of that curve. And another observation we can get from here is this A at a high miss rate of tracking system corresponding to low miss rate and high false alarm rate. So it's kind of inversion of two curves. And this slide shows the amount of effort, if we can improve, or the amount of effort that need to improve the first story detection from here to, for example, there will be 11% at 31% miss to 1% false alarm at 31% of miss. That would be equivalent to the effort that reduced the error rate for tracking from 17% at 0.2% false alarm down to 1.5%. That would be a huge effort, but this is equivalent. And even at this point, if you have a first story detection curve down here, some people may not be satisfied with that result, but actually it is as difficult as if we have a curve here for the tracking result. And let's go back to the tracking task. From the evaluation of last year, we all get this kind of conclusion that ASR, automatic speech recognition, does not hurt the performance. That is partially because that this is the area we are interested in because of the evaluation metric. That's weighted average of false alarm and miss rate. So of course, in this area, you don't see a big difference between ASR and closed captioning. But if you're looking down at this corner, the lower part of the curve, there is a difference. And ASR seems to be hurting the performance. And if you remember the two slides in the past, this corner is related to the upper part of the curve for the first order detection. That may explain part of the reason why, as in Charles' plot, that ASR is a little bit worse on the upper part of the curve. So what we learned is the cluster-based first story detection approach is probably bounded by the tracking technology we have at this moment. And ASR impacts differently with different tasks. So for some tasks, ASR is not a big issue, but for some tasks, for other tasks like first story detection, ASR could be a problem. And of course, TDT tracking is not a solved problem yet. If we can improve the tracking system, then that means we can also improve the first story detection. And we need to try other approaches rather than the cluster-based, because if the cluster-based tend to have bounded by the tracking technology. Okay. Yes.
What's N?
What?
What did you use for N?
Here, the little n is at this given point, how many topics you already seen in the past. That's little n. And then the capital N is how many topics in total is in this corpus. And
What did you use?
I use 400, because based on the estimate that for each topic, there are about like 40 to 50 stories. So for any 2 months period, which is 20,000 stories, I would say this ends around 400 or so. Yes?
Has anyone looked at the issue of how well can one human being do this task with respect to a different human being, Judge Brelin showed this?
Not yet, but James claimed that if he read even 10 million stories, he can still spot a new story coming in.
I mean, to put this in perspective, Medline occasionally makes a clerical error and indexes the same document twice. And they carefully catch when they catch these situations later in their production process, they carefully look at how well the two indexers agree. And the answer is about 50%.
Oh, 50%.
So,
That's not saying, is this a medical article on a topic we've never seen before? That's something saying, what are the topics this is about? Remember, this task has no topic assignments associated with it.
I understand.
So they are different tasks. And
I understand, but I do not believe that they could be done perfectly by one person with respect to a seconds per person judgment.
about is this new?
Okay. Yeah. Any other questions? Thank you.
Are you suggesting that we stop working on first story detection and just focus on tracking?
No, I'm not saying that. I think we need to work on both. We need money for both.
What you said, you're saying it's the same problem.
No, just wait.
No,
I've got that in a conclusion slide,
you're saying it's the same technology.
sort of.
Well, at least
Let me get to the 2 slides from now. So I'm going to do a real quick wrap up, and then there's a future work presentation by Victor Lovrenko. So what I'd like to suggest is that we'll just sort of plow through that, and then we can have some questions and answers. Then you'll realize we won't have even touched on new information detection. So either at that point I'll just show you the conclusions, or I'll zip through this within 5 or 10 minutes or something like that, because there's not a lot to say here. There's a lot of discussion that could come out of this, but there's not a lot that we have to say in some ways. So what did we accomplish? What did we learn in this workshop? Well, one of our major accomplishments, we think, is that we've created a corpus that should be very useful for first story detection. We've cleaned things up, we've added additional topic annotations to it and so forth, so we think this is more useful for the task. We're working with the Linguistic Data Consortium to try to make sure this is available, a nice clean corpus for other people to look at this problem. One of the things we discovered was that this topic generation approach, by having people search for topics rather than doing an exhaustive thing, appears to have been very successful. And we didn't do a deep analysis to figure out how successful it is, but it appears to have been quite successful in a preliminary analysis. And this suggests that it may be a useful technique for doing a much more detailed annotation of a corpus to get a much better understanding of how these news topics work. We spent a lot of time working with various approaches, and we determined, surprise, surprise, that traditional vector-based information retrieval approaches are okay. I can hardly say they're great, because the debt curve never really came very far down. The nice thing about the vector space models compared to some of the other ones we looked at is that it does not appear to be highly sensitive to parameter choices. I mean, you can make really bad parameter choices, but within the realm of reasonable choices, that doesn't seem to be very sensitive to it. We did find that the one nearest neighbor approach, sort of a single link, not doing any agglomeration, was a little bit more effective and noticeably more efficient than the techniques that do all the clustering. And that's kind of nice. It's nice to know that you do about as well with the easier techniques. It's very clear from our experiments that named entities are useful. They contain useful information, but we don't yet really know how to use them. And they're not a panacea. They certainly don't contain everything. There's some very nice failure analysis there showing that that's not true. We did some work developing some probabilistic models and some various different types of probabilistic models and explored those. The nice thing here is that we found probabilistic ways of looking at the problem that achieve effectiveness that are comparable to the vector space, more heuristically inclined methods. So we have a nice formal framework with which to do things. We showed that the ASR errors do have an impact in this task, that as compared to the tracking or the information retrieval task, the ASR errors do seem to have a larger impact here. And we began some investigations into looking into what might be causing that problem. We also explored some methods for doing system combination. I'd say there is we've got some nice background work, but the results so far are rather inconclusive, and we're not quite sure how to do it. It may be that the systems just aren't different enough yet. In my opinion, the largest contribution that we've come up with is that we have some evidence that a topic-based clustering approach to this problem is a dead end. Now, this doesn't say that first story detection can't be done, but we had a lot of empirical results. Remember, we did really well for the first couple of weeks, and then we couldn't do a lot better. So that's sort of empirical evidence that it's hard to do better, at least. I mean, you can also say we're just searching in the wrong places. The failure analysis suggests that there are some things that's just almost impossible to work around using these simpler techniques, and we need more elaborate techniques for it. And this reduction to the TDT tracking problem suggests that an approach that uses the same technology that the TDT tracking problem uses, inverted, is a dead end. So this says as long as you're trying to gather everything into topics in the past, if you insist on gathering everything into topics, what you're really doing is tracking and noticing when you don't track anymore. And that sort of approach appears to be limited. Obviously, any technique that causes a dramatic improvement in tracking would also cause a dramatic improvement over here, but it may be that what we need to do is look beyond these sort of simple unigram type clustering techniques and find more interesting ways to be able to look at the problem. So Victor Lavrenko is now going to talk a little bit about some future work that he's interested in doing over the next year or so.
Could I ask you a question?
Yes.
I don't know the name, and Charles will probably help me. There is this guy at NSA who does trigrams and tries to determine topics with trigrams.
Yes.
What is his name?
Mark Demish.
Yeah. Have you ever thought of these, you know, I mean, this is fairly controversial, right? You know what I'm talking about?
Engram approaches.
Strings of characters.
No, he uses this elaborate tool of this, I don't know, of distance computation of various documents from each other, and he's got it visualized. And do you know who I'm talking about?
I don't know this work. I mean, I may know the work, but I don't. It's not coming to mind as you're saying it.
Well, the point is that somebody who I visited twice was claiming that, you know, that the trigrams are a great way of distinguishing.
I think Jerry Salton tried this decades ago, and it doesn't work.
Yeah, but he may not have had the computers available. I mean,
I mean, in a sense, the closest we
I'm
came
not
to doing
pushing
that
it.
was,
I'm just pointing out that there is this, and he's very vocal about it, right?
we played around with phrases. So looking for, now in this case, we did it mostly with using a parser to look for noun phrases, a shallow parser.
Right.
And it doesn't hurt, but it doesn't seem to help a lot. It helps in some topics very nicely because it turns out it sort of pulls out an important concept. And it may be that trigrams would capture something similar, and it may be that a more rigorous statistical look at trigrams would even do better. There's a lot of evidence in IR that they aren't that useful. But then again, basic IR techniques don't solve first story detection, so maybe they would be useful in that sort of a sense.
John Yammer defined trigrams, and this is from reference.
Yes, well,
He was getting some success with the background models, but not for the topic models, which is probably what the data to train them on. So I don't know how this guy trains on the trigrams.
I may find
Trigrams in a topic context are tricky because you're forming a topic with very little information. But maybe sort of in a more general English model would be okay.
You know, are we going to come back to your conclusion later?
Yeah, let's do that in the context of the future.
So this is a very brief presentation of just a couple of ways where I think we could push this technology further, and what I would like to do to push this further. First of all, I think there is a lot to be done in formalizing our current approaches. So we've hit the limits. We have a system that performs with, at the given level of performance, and we don't expect to improve these methods all that much. But one thing that can be done that will be very helpful later on is if we extend Dan's work on coming up with a formal framework for the idea, it will be much easier to incorporate these approaches into bigger schemes, if we ever come up with bigger schemes. So that's one piece of work that I would like to continue. And the second one is exploring whether we can come up with new paradigms for detection, with new ways of computing similarity, with new ways of detecting whether something is new or not, that perhaps could break the limit that is currently imposed by the tracking task. And in particular, I would like to explore the domain-specific nature of broadcast news. Namely, broadcast news are not the same as general text, and the techniques that we have applied up until now would work on basically any text. They do not target broadcast news specifically. So in terms of the formalization, again, formalization is necessary if we want to use current results in incorporating them into bigger schemes. So first of all, the problem with classical IR approaches is, what do our scores represent? So for the clustering system, the confidence levels that we output, they do not have a clear interpretation. Whereas if we considered a probabilistic approach or an information theoretic approach, to the problem, we could have a much clearer interpretation of the scores. For example, probability of new given a story, or the relative entropy. Another thing that I think could be very useful in this task is if we take certain heuristic techniques that have worked very well in information retrieval and try to formalize them. So for instance, one thing that we tried during the workshop is using what is called query expansion. This is artificial expanding of a document with statistical synonyms. And we did not get the results to work perfectly. But one of the reasons that maybe we did not get this to work is because we don't know how to incorporate it very well. Query expansion is an ad hoc technique. If we were able to formalize it, for instance, as an intelligent sort of smoothing or backoff for a language model, maybe we could get an improvement. Other issues that I would like to look at in terms of formalizing the current approaches are the issues that were looked by Ken Church and Steve Lowe at Dragon Systems, and that's the functional forms of word distributions in the different documents. So people have looked at whether the binomial or the Poisson is sufficient at representing background models. I would also like to continue that line of investigation, looking at whether these distributions are applicable to within topic document term distributions, and also on a smaller granularity than a topic in a core event. So remember, a topic is defined around an event. So what if you consider the stories that discuss that core that that makes a topic? And one of the questions is, does it matter at all? And I think this would be very useful to know. So in terms of breaking the barriers that we seem to hit in the first story detection, I would like to explore a little bit of an event structure of broadcast news. This is something a little bit more domain-specific than general text approaches. So one thing that we have available that no systems have really utilized until now are the rules of interpretation given by the LDC. What these are is these are guidelines that partition the events into general categories. And LDC defines 11 general categories: crimes, elections, natural disasters. And there's a rule of interpretation for every topic, for every event defined by the LDC. So the question is, could we use that information somehow? How could we use it? First of all, we need to be able to predict which rule applies to a given story. And that can be done with several machine learning techniques. And once we have predicted the rule, there's an issue of how to use it. So the rule basically describes what kind of things would be relevant to the topic. So for elections, it's all the campaign work. For crimes, it's the investigation, the trial, the crime itself. The question is, could we use those things somehow? One simple approach, if we could predict what rule to use, one simple approach of utilizing this information is just train different models for every rule. So classify incoming documents into streams that correspond to the given rules, and then use the same general model, but train it specifically for the stories in a particular rule. The question is, could we get better performance this way? Another way of utilizing this information is if we look at what events are about. So in Rose's work, as she has shown, events usually are about who, what, when, where. So named entities do play an important part, but the catch is different named entities are significant for different types of events. So for instance, if you have a crime, it's really important to know who did it and who died, or those things. But if you have a natural disaster, the people involved are usually not as significant. What matters much more is what happened and where. So you could use different types of information. Another way to do this is, and this is more of an abstract approach, this is highly uncertain whether we could do this at all, is by looking at the rule of interpretation, try to come up with an expected performance of an event. So if you have a topic describing a crime, then you expect a certain sequence. You expect it to evolve along certain lines. Like you expect first a crime is committed, then there's an investigation, then there's a trial, and there's something else. The question is, could you model that formally somehow? So in conclusion, we'd like to push further the work on novelty detection and specifically first story detection. And the two directions along which I think it could be advanced is, one is formalization of the current model so that we can incorporate them in bigger schemes. And the second one is exploring the domain structure, exploring the event structure of the news. Questions?
Any specific questions for Victor before we go back to conclusions?
I mean, even done, the first step in this would be simply to say, let's take all the dates and all the places, and instead of treating them as if they were random words, apply metrics to them. Because for those you do actually know, not just same or different, but distance.
For names.
No, not names,
Oh.
places and
Oh,
dates.
places. No, we haven't done that. Not at all.
So take advantage of the fact that things are geographically near each other.
Well, just take advantage, like, normally all you can say about two words is that, you know, either they're the same or they're different. But here you can actually say, if you're comparing two dates, they're either close or they're far. And you could, and
Yes, sir.
you can also make use of the obvious fact that a story is much more likely to be new if it is either far away in distance or far away in time, as somebody asked before.
In drama, people feel that maybe there are only 25 stories of all times, right? And you can get books and, you know, movies and drama, and it falls into 25 plus. And so,
Only two.
well, I'm serious about it, and there are books which, and people in drama departments believe that. So maybe there are only so many and so many stories. And for those stories, you would have those rules that Victor is suggesting. In other words, story number A would have this and this rule, and story number B would be, and then you would have only 25 detectors. And,
There's a catch in the 11 rules defined by LDC, actually. The rule number 11 is other. So
so I didn't mean rules like that. I meant that if you typify the stories, and in one of them dates would be significant, and in another one names would be significant.
Yeah, 11 topics. I mean, there are 11 rules of interpretation to cover 200 topics. So I think it's a reasonable conjecture that there probably aren't that many types of topics. And deciding what you're really interested in might be a little tricky. And I think that's the idea Victor is building on. Maybe you can do something with that.
That brings up a question I had, which I think that all of these frameworks that you're proposing have a flat classification where you're partitioning things. I think, in fact, what's happening is you have hierarchical levels of stories. You have stories about the United States, stories about the judicial branch, stories about the Supreme Court, and so forth, and they're arranged much more hierarchically. And if you're thinking of an application, what's going to happen is you're not going to have people who are just interested in sports stories. They're going to be interested in baseball stories or tracking the Mark McGwire story last year or something like that. Have you thought at all about incorporating some kind of hierarchical notion of clustering, or some kind of query relative topic tracking, rather than, so it looks to me like what you're doing is building one system for everyone that detects new topics, rather than having somebody say, here's the set of things I'm interested in, and then tracking relative to that. I realize evaluation is going to be almost impossible.
But I mean, this doesn't really fall directly into Victor's stuff. So there's definitely an issue of granularity in these topics. And the folks at CMU in particular spent some time looking at that.
It's more than an issue of granularity. I mean, this is a big, I mean, the discussion of what the topic is sort of overwhelmed the TTT program at the outset, and quickly decided that doing some kind of topical organization like you're suggesting was something we didn't want to get involved in. Actually, the whole research task was redefined in terms of detecting events. Who, what, where. You know, something happens at some place at some time. So, you know, the whole term topic, I think, is a bit misleading because it's all oriented toward events.
But, so the thing is, there may be an event that's the seed of it, but the topic is fairly large in that sense. And I mean, the closest I think that we've looked at in this work is what Victor was just talking about on the previous slide, of saying that maybe some of these types of topics fall into specific sub-events or subtopics or something like that, and maybe you could use that structure to try to classify things. That might interest you. Carnegie Mellon, Yiming Yang, and Jaime Carbonell spent a fair amount of time looking at issues of hierarchical clustering when they were building up these topics. Now, in this particular task, we're not building up topics. But they, you know, it seems fairly obvious that in terms of a large topic like the Asian financial crisis, you may not be interested in everything in the topic. You may be just interested in the stuff that happens in Japan, or something like that. So you may want something that breaks it down to a finer granularity. What we've done in all of this work is sort of abstracted away from that and said, interest doesn't matter at this point. So we've taken a black box approach and said, if I can track anything, then I can put a little information filtering engine on the front or queries somewhere and only track the things you're interested in. Now, exactly how to integrate that those two ideas isn't clear. Do you find what's interesting and track it, or do you track and then find what's interesting? But essentially what we decided to do, just for the sake of simplifying the problem, I think, is to ignore interesting. It's a real tricky one.
Just to add, this whole thing in fact led to a whole underground activity in our part on building multi-hierarchies of topics. So stories actually belong to more than one topic at different levels in the hierarchy. And you can display these in neat ways and navigate them. But there's one of the things about that kind of work is that there is no way to know if what you're doing is useful unless you have a task. And then you can measure it with respect to that task. And the whole TDT thing is meant to be not just a single task, but a technology that cuts across multiple tasks. So that's why that activity kind of diverged from the main TDT activity.
I wanted to sort of ask Victor a question. To what extent do you think the current database, which is a 6-month window essentially, is going to be sufficient to support the kind of research that you want to do? I'm wondering if at some point you're not going to get back into this, the data limiting the kinds of things that can be accomplished. And maybe it might be appropriate as part of the follow-on research to have LDC generate more data to overcome some of these deficiencies. I think particularly in the named entity stuff, that would be very useful.
In terms of, well, it's hard to say in terms of whether we'll be able to get new data. I don't know if we will have new corpora for subsequent sections of TDT. So for TDT3, we do have a bigger corpus, but that's mostly due to Mandarin stories. So that's a completely different
The
dimension.
TDT eval set is the last 3 months in 1998, or somewhere in there.
Oh, okay, so we are getting more data.
The corpus is growing. I mean, the TDT corpus is growing.
But you need it annotated in a particular way, right?
Right, so there'll be some topics added in. One of the problems I see is that there's a gap in here. We've got January through June, which is nicely annotated, and then there's nothing July, August, September, and then there's going to be some stuff that's annotated for the last quarter of the year. So there are topics that are being created in that. That's the eval set for the TDT3 task, which will be used this fall.
So do you think the current database, if the goal, one of the goals of the follow-on research is to establish a research paradigm for this kind of thing, do you think the current database is sufficient to do that?
I think it is. Hopefully we will get more data, and with more topic judgments, with more topic annotations, I think we will have enough data.
May I suggest that you do something in the last 1 minute?
Okay. So we also worked on new information detection, which is this within story idea. So just to make it clear, I'll just illustrate it. You're given this story. You're interested in the Carla Faye Tucker execution in Texas. She's the first woman executed in Texas in 100 and some years or something like that. And she'd converted to Christianity, and people thought maybe it should be executed. Well, if you get this large thing, maybe what you're really only interested in is stuff that's new, so what you'd like is a system that does something like that. Shows you the story and says, here are the parts in it that are interesting to you. So every time a story comes up, it can show you the parts that are interesting. So we worked with the LDC, we used the TDT topics to create some test ideas here. We had the LDC, we did some preliminary tagging, and we had the LDC mark this to see what they could do. We were interested in looking at a few things. We were going to do things with vectors, sort of based on the same ideas as the first story detection. We figured we'd have to expand sentences, that the sentences on their own are going to need some sort of work to flesh them out because they're usually kind of short. And so maybe that would be some nice statistical stuff, or use with thesaurus, or maybe we'd have to do some natural language processing there. But there's a big problem, because after we got the LDC to do this, all of our pilot studies seemed to indicate it would be reasonable. When we got the LDC to do a larger set of stories, we ended up finding out that 80% of the material was new. So that meant that with an algorithm that isn't particularly successful, because we're not going to be perfect at this, we could remove 20% of it, and it's not clear that there's a lot of value in that. So what this meant is that we spent a lot of time, particularly in the early part of the workshop, trying to figure out better definitions of new. What does it mean for a sentence to be new, for information to be new inside a story? Because we don't believe that 80% of the news is new. All you gotta do is watch headline news to know that's not true. So what you look at something like this, so here's a bunch of stories that are all on the Clinton fundraising scandal, the Chinese thing, and in fact, each of these is marked new. So they're in the order they came in. So there was this one and then these four, and they're each marked new, but they really don't say that much that's new. Except if you look at it carefully, you can see that each of them sort of raises a subtle point. So this says what the allegations were and the number of allegations and things. So each of them actually does contain some new information. So even though we felt it was wrong, what did that, we felt this number is wrong, but when we looked at it, it seemed like, well, maybe in fact it's right. So what does this really mean in terms of looking at the problem? Well, it turns out that in fact there is a lot of information, and there's a lot of new information in news, but almost all of it is really tiny little bits and pieces. But they have to have some reason to publish the story, right? So there's something going on. So if you're not following, if you're only vaguely following a story, you don't care about all those little tidbits. If you're kind of interested but not really that interested, you don't care about the tidbits, you want some sort of higher level version of that. And if you're not even interested in the story at all, obviously you want the whole thing suppressed by the tracking task or something like that. So we figured we need to do some work to redefine what new sentence meant, because that was how we were looking at this, was a sentence new. The biggest problem, we suspect, was the sampling. Our pilot study suggested this would be okay. We wanted a set number of stories per topic, and so for the large topics, we sampled evenly throughout the space. Big mistake. For something like the Asian financial crisis, which has almost 1,000 stories, that meant that every story had a minimum, when you go from one story to the next, you had a minimum of 2 days in there, and sometimes 6 days. That's a lot of time for new stuff to happen, and there were a lot of stories intervening, obviously. So by sampling sparsely, we sort of shot ourselves in the foot. There were some problems, or technical problems. There's sentence fragments in there. You get sentences like, these 3 sentences were in a row. The passages were, colon. Maybe this is the good sentence break. Did she and Brian go to the motel after give birth to a baby? End of sentence. Then the third sentence is answer no. Well, is that sentence new or not? And it's a very difficult one to figure out what that really means. And there's other things that just make the problem very messy. And so what we looked at was trying to find mechanisms or rules that could be used to try to collapse things together so that things that were strongly related to each other ended up, or they really definitely belonged together, could be treated as a unit rather than broken out. There's also this big issue that sort of crops up in that slide, a couple slides back, about what's significantly new. It's not just whether it's new, it's whether it's significantly new. And unfortunately, significantly new means something quite different to people in different contexts. Like I said, if you're not interested at all, if you're vaguely interested, or if you're very interested, each of them is going to have a different notion. So at some level, in the sense of Karen Spark-Jones' talk last week, this is saying that there's a lot of context-dependent stuff going on here. It sort of depends on why you care about new information detection. So what we concluded was we spent a lot of time examining the task, and we found a lot of problems, and some of them seem like they're easy to fix. But even when we did our best approaches, we resampled some large topics. We did sentence groups over the loan sentences to try to deal with that. And we tried to make new being more important. It has to be, the main thrust of the sentence has to be new, so little tiny clauses won't matter. Even then, we were only able to make 50% of the material old. And that's a lot better. I mean, at least removing half of the stuff would be good, but we're still suspicious that we haven't quite gotten there yet. So we think we have a better understanding of the problem. There's a lot of new information out there, but figuring out exactly what is new and interesting is a very tricky part. And obviously, the early stuff wasn't going to work very well. Some of the things that we feel that the task probably needs to be completely redefined. And so some ideas that were sort of bounced around, and we haven't investigated any of these. One possibility would be to look for subtopics in here. So look for shifts in the topic. This would be sort of high-level changes in the event. Another interesting one that someone raised was the idea that maybe when you're asking for new information, what you really want to know is if somebody asked a question early in the topic that got answered later on, that what you want is to know that it was answered. And so maybe that's a version of new information detection. So if someone says, who committed this horrible crime? And then later on you see the answer to the question, that would be a nice thing. But if nobody asks the question, then why bother, or something. Then you get to things that are a little trickier, like one possibility, and this is not at all new it's not a new idea in a sense. One possibility would be to try to label topics or perhaps subtopics with the central idea. What is it about it that sort of describes what it's about? This is sort of a flavor of summarization. It's far from an easy problem. And another one that was suggested that I think is interesting, although it's a slightly different take on the problem, is to say, suppose someone reads one newspaper or watches some news program consistently. And so they promise to always do that. And what they're interested in knowing is what new material is presented by other sources on that same topic. So I read the New York Times, tell me what CNN has to say that the New York Times didn't say. So it's a different take on the problem, and it may be that, particularly if your reference source was big, you may get a lot less new information out there. So that was it, and so overall, we tackled two problems in novelty detection. For the new information detection, most of our work was looking at how the problem should be defined and trying to get a better understanding of it, because the original task turned out not to be profitable. There's a lot of effort, we put a lot of effort into first story detection. We built a system, we looked at a lot of issues, started some probabilistic framework stuff, and I think most importantly showed a probable bound on it. And this isn't as good anymore because we showed it in the ad, but of course we learned the joy of, oh, I turned the speaker off too. We learned the joy of novelty detection. So that's what we did this summer.